Welcome back to Wood Engineering. I'm Jeff Orochko from Carleton University, and in this video we are going to talk about how to design bearing surfaces in wood and timber. So when we're talking about bearing surfaces, we're talking about usually when we have a piece of wood, it has to sit on something. If it's a column, it will sit on its end grain, and that would be compression parallel to grain. What we're talking about is if I have a beam, for example, and this beam has to sit on something, then it's going to load this piece, it's going to load the piece of wood in the perpendicular to grain direction. And that could be like this, or it could be the flat like this. Since wood is orthotropic, could be either side that I'm loading in order to get perpendicular to grain bearing loads. So it's usually because one piece of wood has to sit on either a wall or a column or some other piece of wood, maybe a joist sitting on a beam, for example. And we're going to look at some examples. So what we're primarily talking about here is compression perpendicular to grain, and that's how you see it described in the standard. But the most common application of that is for bearing, one piece of wood bearing on another. So if I'm looking at this piece of wood here, we're talking about the case where we are putting load on this side here, or could be putting load on this side up top here. But we are not talking about the case where we are putting load on the end here, because this is compression parallel to grain. Which we already talked about when we talked about design of columns. So what is the failure criterion that we are looking at for design of bearing surfaces? And when we're talking about design of bearing, compression perpendicular to grain, we're talking about squishing the fibers, right? So if this bundle of straws is like my wood fibers, then when I'm talking about compression perpendicular to grain, I'm talking about crushing in this direction, which has the effect of smushing the fibers. So then there's a bit of a question about, how do we then define failure? Because I could just be smushing the fiber on the outside, and I mean, I still have stability, and the piece of wood is still, it's still not going to fall down or anything like that. So since this is kind of a local effect, how do we define failure? Well, the failure criterion for compression perpendicular to grain actually happens to be a deflection criteria, which is a little bit strange, because even though it's a deflection criteria, we are going to treat it as if it is a direct strength criteria, and we're going to see how that's done. So as I just mentioned, our deflection criterion is a limit to the deformation, and the limit on that deformation is actually 1 millimeter. This seems a bit arbitrary, but this makes sure that all the bearing surfaces don't have any significant movement under their design loads. So I'm going to draw exactly kind of what this looks like. Okay, so here we have one piece of wood sitting on top of another piece of wood, and the piece of wood at the top is coming in and out of the plane. That's why I've drawn the X. And it's bearing on another piece of wood, which has a grain direction that is like this. Okay, so this is I'm just showing the top of this piece of wood here. Okay, and when that piece of wood goes down, it smushes the surface fibers down, right? But it's a bit of a local effect in that not all of the fibers throughout the thickness are necessarily affected, although there are some important cases where they would be. But you'll see that it's kind of a local effect where we have smushing of the fibers near the surface, and then eventually the fibers below kind of remain straight. And the limit on this deflection is that this deflection that I'm showing here in green is less than 1 millimeter. So all of these things are the wood fibers, just shown kind of schematically, and these fibers are crushed perpendicular to grain. But on top of them being crushed at the surface, they're also kind of deflected. So if I'm just looking at what's happening to one of these fibers near the top, at the middle, it certainly gets smushed, like the straw gets crushed. but also when we're pushing down, there is a deflection happening as well, right? So the fiber at the ends is held up, and then in the middle, it gets deflected downward. And this provides some interesting local effects as well that we're going to account for in our equations, the fact that these fibers get deflected downwards. So now that we know what's happening, we want the compression perpendicular to grain strength to be set up kind of similar to all of the other equations for strength, compression parallel and tension parallel and bending and all those things. So the way that the standard is set up is that it actually still defines, even though this is a deflection criterion, it still defines a strength FCP. And how does it define that strength FCP? It defines it based on, this is the stress in the fibers when it reaches 1 millimeter of deformation. So what does that look like? So basically what happens is, as we're loading the surface of the wood in red, and the brown is kind of the surface, you can see we deflect it down. As we increase the stress, and it's the stress in the wood, right? As we increase the stress, or which is equal to the applied stress, you can look at either side, right? As we increase that stress, right, our deformation is also increasing. Or as our deformation is increasing, which may be a better way to say it the way I've set up this axis, as the deformation is increasing, the stress is increasing, and it increases and increases and increases. And we can consider that as going to be something perhaps close to linear, even though likely it's not entirely linear. At some point, we're going to reach a deformation of 1 millimeter, right? And at that point, we're going to define that when it reaches that point of 1 millimeter, our stress perpendicular is equal to our defined failure stress for compression perpendicular, FCP. And FCP is the value that we're going to get from our table. So if we look at these equations, that's kind of the simple way to think about it, but then there's some other wrinkles in here that we are going to need to consider when we look at the strength. So this deformation is also equal to a strain times a length. So you guys are familiar with this. Strain equals delta L over L. So if I rearrange that equation, I'm going to have strain epsilon times a length, right? So that's basically the deformation of deformation, the definition of deformation in one dimension, right? So deformation, if this is delta, and this is strain, and this is length. Okay, then we have deformation as strain times length. We also know that our strain is equal to our stress divided by our Young's modulus. So this is also back to simple mechanics. So this is our stress. This is our Young's modulus. Okay, so if I combine these together and I find deformation based on the stress now, I get that my deformation is my stress, which is my perpendicular stress, times my length, which is also perpendicular to grain, times my E. So what's this L that we're talking about? The L here is the length over which that deformation occurs. So that can change, right? So if I come back to here, right, my L is some percentage of the total depth of the member, right? It's not going to be the total depth of the member, nor is it actually going to be linear. It's not like this part L is exactly deforming and then this part is not. Obviously it's not like a yes or no, but let's say for now that we're talking about we have some section that's deforming and the length of that section, that's maybe it's more of an effective length, is L. Okay, so this is L perpendicular is the length over which the stress acts. And since it comes into our equation, we know that this parameter is important. Now, this is not exactly how these equations are derived or anything. I'm just looking at kind of a simple mechanics model to illustrate how the length over which the stress acts in the perpendicular to grain direction is important. And the reason that it doesn't act everywhere throughout the depth is because that stress has to go somewhere. So usually it's going to some kind of reaction, so the principal direction of the stress is going to turn. We're going to see that in a minute. Okay, so if I then look at rearranging this in terms of stress perpendicular, right, I get E times delta over L, where I'm going to, if I'm considering that this is my limit state for perpendicular to grain strength, then we're going to say that this is FCP when delta equals 1 millimeter. So I'm basically saying my strength is the stress perpendicular when deformation equals 1 millimeter. And this one is a material property, so that doesn't change. And so we then need to know how much of the beam depth, how much of the beam depth is actually experiencing that perpendicular to grain stress. Okay, well, it turns out that this depends very much on how exactly the beam is being loaded and where the loads are starting and where they're going. So we're going to look at two different cases for this, and these are the two different cases defined in the standard as well. Okay, in the first case, we have a localized compression, and we just have a short depth, and I'm going to show what that looks like. Okay, so here we have a beam. I'm showing it as a pretty deep beam just so that we can get a visualization of the which way the kind of stresses are going. But it really could be any beam. And we have some load at the top in the middle, and then we have some supports which are located somewhere away from where the main vertical load on the beam is. Okay, so if we were to look at which way do the principal stresses, the principal compression stresses go, at the top, I mean, we have definitely stress going straight downward, right? And at the beam reactions, we know that there has to be compression stress as well that's holding up the beam, right? Compression perpendicular. But in between these, we have some movement, some turning of the principal compressive stress, right? It has to turn in order to get from where the load is being applied all the way to where it's being resisted, right? So we have some turning of that stress field. Okay, and it ends up getting shared on each side, right? So, you know, if we're looking at the bottom of this beam, for example, here, right, we know instinctively that there is going to be no compression perpendicular stress here. Down there, there's only basically tension stresses along the length of the beam, right? So there is some zone underneath this load, right, where we have actually compression perpendicular. So we have a zone under compression perpendicular. And at the reactions, we'll also have a similar zone. Now, it's not going to be perfectly compression perpendicular throughout that zone, but let's say there's some effective zone where we have significant amount of compression perpendicular forces, even though they're in the process of kind of turning directions, right? So same here. Zone under compression perpendicular. Okay, so if we look at what is the principal kind of, where is the direction of the compression, the principal compression at the reaction, it's something like this. In between, it's something like this on an angle. And at the end, it kind of turns again to be vertical, more or less. But that's why we're getting big shears in the beam in between the application of the load and the reaction from the load. Okay, so here the compression direction changes. Okay, so you have to remember back to mechanics. So if I'm looking at what is the L, then underneath this load here, I have some L, and and it's definitely not the full depth of the member. So we have some L here, some effective L, and that L is the L that I was talking about back here, the L over which that stress acts, okay, to create that 1 millimeter deformation at the top. Okay, and this case here is what is called in the code, or in the standard, they'll call this effect of all applied loads. Okay, so I like to divide it up here in terms of basically, this is what's happening to the compression stress field underneath where we're bearing. This is the kind of situation we're looking at, because we will always get a localized compression perpendicular stress when we have bearing, but we won't always get the second effect that I'm going to show right now. So let's say that this time I have a similar kind of beam, maybe same geometry of beam, but instead of the load being applied near the middle like it was up here, now the load is applied near the location of a support. Now, this is not the only case where I'll run into this kind of situation, but this is kind of the most common case, which is why the standard calls this case the case for effects of loads applied near a support. Okay, so in this case, I have loads coming from the top, and those loads, since they're basically applied directly over the support, none of those loads get transferred over to the right reaction point, right? They're all going directly through the beam. So if I'm looking at the stress field, the compression stress, principal compression stress, basically they're just straight lines going right from the top straight to the bottom. So what is the zone that is under perpendicular compression perpendicular stresses? It's basically this entire area here now is the zone under compression perpendicular. So now that means instead of my L being localized just below the support, I basically have an L that goes all the way through the full depth, right? And I like to call this is not a technical term, but I like to call this case the squeezing case, or the squishing case. So sometimes you might hear me refer to this as a squeezing bearing load, because it's squeezing it not just from one side. We're not just pushing down in the middle here, but we're actually squeezing it one side to the other. So the entire through thickness of the wood is experiencing that compression perpendicular to grain stress, which means the entire length of that wood is being strained. The entire depth of that wood is being strained. So that means what happens to this equation? So my deflection criteria, delta, is the same. This one stays the same. This one stays the same because it's a material property. But now L is going down, going up significantly, right? Which means that what? Now my my perpendicular to grain stress at that deflection has to go down, which means I need to set my stress limit down a bit lower, okay, to account for the fact that the full depth of the member is now being stressed. So that means it's going to deflect a lot more for the same amount of stress. Okay, so if I want to limit that deflection to a certain limit of 1 millimeter, I have to limit the stress as well to a lower limit. And that's exactly what the standard does, and we're going to see how it does that. Okay, so to sum that up, you know, recalling this equation, delta over L, larger L, lower perpendicular to grain stress for the same deflection of 1 millimeter. Okay, so what do we do in the standard? So in the standard, they apply a factor of 2/3. You know, based on test data, this is an approximate reduction, so they're going to reduce the strength by 1/3 in order to account for this effect of squeezing, only in the cases where we're experiencing that squeezing. So if I don't have the squeezing, if I have a case like this, I don't apply the 2/3 reduction. If I do have the squeezing, I have a case like this, then I'm going to apply that reduction, that 1/3 strength reduction. And it's easy as that. So I just have to be able to recognize when we're in a situation that we're encountering that squeezing force. So in the standard, it comes up with 2 perpendicular to grain resistances, QR, which is the effect of all applied loads, which we're going to look at, and then QR prime, which is the effect when we have the squeezing. So it's the effect of loads applied near a support. And the way that 086 treats this, the Canadian standard, is the exact same for lumber and for glulam. So there's basically no difference between the two, except you're going to get your strength, FCP, from a different table, depending on whether you're doing lumber or glulam. And so the equation looks like this. So for effect of all applied loads, this is the regular one where we're not near the support. We have a phi factor to reduce material strengths. We have capital FCP, which is the strength FCP, but modified for duration factor and service condition and treatment factors. And we have AB, which is the area of the bearing. So we've looked at things in terms of stress so far, but obviously the actual strength in kilonewtons is going to depend on what kind of area that stress is acting over. Then we have something called the bearing factor, length of bearing factor, and we have a size effect factor. So this one here is bearing area, which is going to be a bit different when we do the squeezing case. This one is length of bearing factor. And this one is our size effect factor. We always have some kind of size effect factor in wood. And we are going to go through all of these in detail, but we're probably going to have to split it over 2 videos in the interest of time. So for bearing, my phi is 0.8, and my FCP, capital FCP, which we're used to seeing, is small FCP, KD, KSCP, which is my service condition factor for compression perpendicular, service compression perpendicular, SCP, and KT. We're in a nightmare of indices here. Okay, so there's no KH factor, you'll notice here. Why? Because KH system effect relies on multiple members holding up the same load. And in bearing, by definition, we just have one member encountering one other member. So there's no need to have KH. Okay, and where do we get this FCP? We get that from our tables. 6.3.1, A through D, if I'm talking about lumber, or 7.3 if I'm talking about glulam. So for effective loads applied near a support, we have an almost identical equation. We have a prime, a little dash on the QR, so it's QR prime, just to indicate that it's different than the QR. And we have this factor, first of all, 2/3, which is different. This is the factor to account for the squeezing, right? So to account for a longer zone under compression, as we talked about, under compression. And the other difference that we have is AB prime, which is a combined average bearing area. And we need to calculate an average area because there's 2 bearing surfaces now. There is one on the top of the member and there's one on the bottom of the member, and they may not be the same size. So we have to have some way of accounting for the fact that that the bearing surface is different on the top and bottom to come up with some kind of effective criteria. And basically the way that they do it is they take a straight average, and there is a there is a limit to make sure that you can't make one really big to compensate for one being really, really small. Okay, and this applies in specific circumstance. So, you know, we've talked about how we need to have this effective loads applied near a support because of when we're going straight through from one to the other. But how do I decide how close those two loads have to be lined up? Well, there's a very simple definition in the standard. So if I have two loads that are more or less on the other side of the member from each other, and they're both causing compression perpendicular, then my criteria is that if those two loads are within D apart from each other, so if the distance between these two is D, the depth of the member as shown there, or less, then I need to consider effective loads applied near a support. And that applies whether we're at the end of the member or whether two loads are near the center. It doesn't matter as long as those loads are close together within D. Okay, so the next thing I want to do is look at some practical examples of applying this criteria and seeing what checks that we actually need to do for a whole bunch of timber elements.